I guess for those of you who are here, you're going to get, you're going to get it all. But we'll see what happens. That is once again to make the explanation to you guys that being present in the lecture, always the advantage. In case I can't record it, then that's it's a situation where you get what I get to talk to you about. Let's go ahead and just briefly talk about like the last couple of seconds of what we were describing on Tuesday. And one of the problems with this class is that it being a Tuesday, Thursday meeting, it just feels like one giant lecture right in the middle of the week, right? But I'm going to try to span some stuff out for you in the effect that I'm going to give you an assignment that hopefully maybe you can start on it over this weekend. We'll see. Obviously, I don't know what your schedules are like, but I'm working on putting it together. I originally was thinking about having you guys code some of this in Python, but at the same time, I think I'm just going to go ahead and give you like kind of a set of instructions and let you just work off what's there rather than having to try to figure it out, because quite frankly, figuring it out at the same time as learning to code it is probably a little much. All right, so what we see from this analogy, which was, it's kind of a fun analogy, just this idea of attaching it to kind of a strange, random, abstract thing in your head, getting that shower temperature, shower pressure just right, as a result of having two adjustable parameters, indicates that there are, in fact, actually two sets of set point characteristics relative to the sensitivity of that individual weighted characteristic or weighted element within the sequence of elements, indicating that the amount that you set the main to changes the relative error with respect to the overall capacity of the system to be set to the point that you're interested in. And there's a relative degree of error, total error within pressure space relative to the error with respect to the handle, right? So the error at the handle is partially responsible for the error at the head, right? So the error at the shower head, some of it's the handle's problem and some of it's the mains problem. So what we have to do is we have to describe a process through which we can analytically, utilizing that mathematical process we've been talking about, which is the gradient descent algorithm, which I've described to you guys a couple of different times, and we've talked about it as far as its generalized purpose. If you get the idea of sort of walking down the mountain, then you should be in good shape on that. But what do we do whenever we have to hand this system off more complicated processes past this level of complexity, okay? Notationally, I was a little ambiguous with the way I described it last time. I even went back and listened to myself because I saw a lot of people with kind of like weird glazed looks on their eyes. So I have another slide in here that tells you exactly what we're doing with regard to the notation, because sometimes I don't always get that as clear. There's actually a superscript and a subscript, and there are in fact two subscripts for notebooks, okay? Bear with me. Okay? So when we think about this in terms of responsibility, we're going to think about, the example that's given is C naught. Now, why C naught is because they're utilizing the term of cost function. Why do we use J typically? I think it's just because of the fact that it's the calculation of the matrix of the gradients is actually called the Jacobian. Okay, so the Jacobian is that matrix form of the gradient distribution, so we use the grad J. So if the Jacobian is actually the array of gradients, then the gradient of the array of gradients is called the Hessian. Okay, that's the second process, the gradient of gradients. Well, I'll show you guys what those are, but I'm going to do that on an online supplement because in reality, that's one of those things you kind of have to pick apart. And so there's a lot of little parts for it. I'll show you some segments of that, and I'm going to let you look through some proofs. I figured proofs, for the most part, are going to be those things that I try to supplement now that I'm trying to make up for a little bit of lost time. But that when I give them to you, there'll be something that's kind of a self-encapsulated item, so it's just kind of studied at your leisure. It will make a difference, obviously, for kind of understanding the whole flow of the process, and anything that I talk about as far as a process or terminology or whatever else in here or on supplementals or slides or whatever, all that stuff's fair game, but I'll try to be reasonable when it comes to what I can expect from you guys. I also do provide and allow for you guys to be able to construct formula sheets, so don't ever panic if you don't feel like you're gonna be able to remember all the terminology for it, you're just gonna have a really busy piece of paper, okay? That's just how it's gonna happen. And it's gonna get really busy, trust me. You'll note here, one of the biggest cripplers, and I think in general for people with this topic, is the notation is visually intimidating. You look at it and you go, there's a lot of stuff there that's very cluttered, right? So what am I looking at? I think a lot of it is the fact that most of us probably haven't spent a lot of time with partials, right? So some of you may have a little bit, if you've done a little bit more physics, or if you've done some stuff with decompositions and Lagrangians, etc., you'll have to spend a little bit more time in that space, right? So we'll talk a little bit about how we undertake the computation of the partials, but not in extreme depth, because we're really looking to just figure out how we do this in compute space, right? I do want you to be able to understand what's happening here, but you don't actually really need to do the partial, right? You're not actually going to go and decompose it. Now, granted, we can provide some toy examples. We can talk about an actual activation as a function. I can see the activation is 3x squared, and you could take the partial of that with respect to the output. And you could do the matrix algebra for that, and you could get a definitive numerical answer. But it would be a toy problem, because it's obviously going to be respectful of some data that's informing that space, which means it's going to be a calculation you don't want to do by hand. Obviously, you're never going to compute a neural network by hand. It's just, there's really no point to it. It's the same way as you don't want to compute a linear regression by hand of anything over probably 5 or 10 items, because at that point in time, as we say, that's why God created computers. So when we're looking at it from this perspective, we say the error function, right, or the cost function, guys, if you guys will just bear with me in saying that cost and error are related to one another, and the effect of saying that if I make an error, it costs me something, right? So if I make the error, it costs me something, I'm going to say the cost of that error is partially due to the activation of some element j at some layer L. And that activation at some element j at some layer L is also equal to the input relative to that layer L from some neuron j, right? And we're going to call this element z here, right? Z is going to be the quantity with which we're sort of getting into or putting into that activation. So there is a quantity that is what? It's the sum of the products. We said that Z is the sum of the products as being fed to A. So A, alpha, the activation, that is the sigmoid. That's the stuff we were talking about to begin with, is Z goes inside the brackets, right, as the summation of products for the array of inputs times the array of weights. You can look at any given layer. This particular item is treating layer L, right, some abstract layer L within the system, with respect to some layer L minus 1, okay? So within the notation that I've designated up there, I say alpha of L minus 1 up in the top. So when I'm passing this back, I'm going to pass it back from activation to summation, product summation, and then also contribute to that product summation as a result of the activation of the previous layer with respect also to the inputs of that layer with respect to their individual component functions, right? So we say that the summation of all of the characteristics with respect to some layer L minus 1 through this system, enumerating all the layer elements, is going to be the responsibility, or the cumulative responsibility, of the cost of the weight arrays that make up the activations in some layer K. So over some layer L is a result of some layer L minus 1. This look vague enough for you guys? Okay. If any of you guys have seen the 3 blue, 1 brown, I really want to recommend it again. I'm not going to talk about this slide because I think he does a good enough job with what he does, but he does it different than I do, at least enough to be able to make a difference. But he explains cost functions, and he explains the idea of a cost function by projecting a number line with respect to the branching factors of the network. So he's taking the network that was normally laying flat moving forward, and then he's projecting it as a flow, feed-forward flow process downward in the process of this expansion, right? Indicating that there is a relationship between the activation and the summations, right? And the summation is contributed to by the weights and the activation layers in the previous layer. So if he shows you the description of sort of, as you crank on those knobs, what happens to the cost function, what happens to the total error in the system, right? If our goal is to get the thing to go that way, how much or in what direction do we have to crank on the weight elements in those considerations in order to try to get it to go in that direction? Now, he goes into a little bit of depth, but like I said, here we can look at these on an individual layer, right? We can say that this breaks down into that previous equation as related to that base summation, and we're going to use the chain rule to represent it. Right, I don't love this particular slide because even though I think it does a good job of sort of linking the topics together, it's not really showing you very spatially what we're looking to do. So there are actually a couple more slides on here, and I'm going to come back to them in a minute. So I hate it, but I'm going to do my bad thing where I change slides halfway through and come back to it later on, okay? So I'm going to actually just pop through all the stuff coming out here and talk about a couple of items that we need to understand in order to be able to calculate some of the items we're going to be going to here in the future, all right? Any linear estimator can be represented by y hat, d hat. D tilde here, right, is going to be what we call the expectation of a linear estimator. The expectation of the local estimate, E, right, is going to be the difference between target and estimator. If I look at MSE, mean square error, right, I've just replaced MSE rather than just E, like we've been utilizing in the previous calculations, I replaced with J. And I make a statement here in the middle. That's probably the first time that we've made it, but it's an interesting one. And that says that if we utilize Gauss's theorem, which states that when you set the relative values of the partials of the gradient with respect to the elements of the linearity operation to 0, right? You're effectively setting the partial with respect to 0 is where? It's going to be where it intersects with the surface, right? So it's the union of that gradient relationship. So it's setting the grade up to where it's going to be flat, right? You set any linearity or even a partial linearity equal to 0. That allows us to be able to decompose the component of the error relative to the bias and relative to the weight system. The normal expressions allow us to be able to calculate the outputs for a strict numerical, right? That's how we would calculate it in sort of the hard expansion process for strict linearity. But instead, we're going to utilize this estimator of the Jacobian for the weight decomposition of a multilinearity. All right, so we don't actually have to do this in a strict fashion where we have to go through and calculate the means and the means of the targets and means of the predictors, right? That's a very costly process. And it's also very costly when it's not possible to fully decompose one factor's convergence and covariance with respect to the other elements in the system. Most of the time, there are actually going to be components of correlation between the features and factors, right? You guys all understand the concept of the correlations between features. Anybody not tracking with me there? Okay. The reason why I say that is because that's basically the reason why we have to use the partial differentials. Is because we respect or we validate that it's unlikely that any independent feature within the system is in fact truly independent. So we're going to have to figure out how they change with respect to one another, how the systems of importance and relevant significance change with respect to one another, and how much our overall estimate within this linearity space is capable of capturing the variance with respect to those feature outputs. This R-square calculation is something that we've talked about a lot within ISL, probably basic statistics class overall. Is the idea of variance capture, or the idea of how well that line does at being able to regress or predict or separate the elements and objects of interest. But I want one thing to be clear here. While these calculations can be done on some particular spaces within some data sets, right? Most of the stuff that we do that has kind of strict linearities or even low dimensionality multivariates. When you get into high dimensionality multivariate spaces, both of these things have to become estimates. They become guesses, best guesses based upon what you have available to you, right? Or however many of the features you're going to plan to use within that space. So whenever we think about it, we say that one line in one space might be really good at capturing one particular aspect of the variance in the system, but another line that on another set of dimensions might not. So we're going to have to balance it. Once again, that's the system where when you have more equations than you do variables, you're going to have to come up with a solution that satisfies everybody, right? Only mostly. I say that training a neural network is the ultimate compromise because you have a huge category of individuals. Everybody has their own independent opinions and preferences, right? And you can't match every single person, but you can do your best to try to accommodate everybody. But what happens when you attempt to accommodate everybody, okay? You end up with a pizza with half pineapple, half anchovies, half cheese, half pepperoni, right? And you just keep cutting it into tinier and tinier slices. What do you end up in the end, right? You just end up with a pizza with a piece of bread with, red sauce on top of it and, maybe some cheese. Like, that's the only way that you can make everybody happy. And nobody's happy, right? Nobody's truly happy, but everybody's happy, okay? Compromise is when everybody leaves slightly dissatisfied. So when we think about the idea of a lot of examples that don't necessarily perfectly correlate with one another, then we're going to do our best to both spread the blame around and make sure that everybody is only as happy as they need to be under the circumstances. So as I said beforehand, gradient surface descent is this process by which we update the relative weights within the system with respect to the computed estimate of the gradient. Why is this not actually the real gradient? Why does it use the word estimate? Because in the same way I can't compute the means, I can't compute the distributions and variances of the entirety of the data set because I may not have all the data, right? I also can only make localized estimates of the gradient. I can't actually compute the entire gradient. I usually can only see what is immediately in front of me. I'm only able to see within a very small area of this incredibly dark, cloudy, foggy space, right? So that localized estimate is what we're attempting to work back to. The estimator is used here, right? Is broken down into, once again, we see here, this is partial with respect to W, okay? So this is the portion of the weight system. And what did we say we were interested in earlier? We're interested in grad J, right? Or J with respect to W. So we've actually just substituted J. That's the only thing we've really done here. What J did we use? Or what metric of J did we use? We're using MSE, mean squared error, right? So the Jacobian, or the instantaneous gradient estimate for that variant J system is approximated by this breakdown of 1/2 times the partial of W with respect to the square of error for some local K within the system. And that is the current weight. So local K is the current time, the current weight at the current time, right? So at some time step K, we're going to call the relationship between time steps something called an epoch. Have I used that term before? Mm-hmm. Okay. When I'm talking about it, I want you guys to keep in mind that if I repeat something, it's usually significant. Sometimes the reason why I'm sort of walking through all this again, why I go through it a little faster every time, is that repetition helps us get the whole scope of the process in training, okay? I'm going to utilize what type of data in order to be able to assess and ascertain this update process. I have 2 kinds of data. What kind of data do I have? What are common ones?
Matrix.
Mm-hmm.
Okay, it's a matrix, right? But where did it come from? I had some data I collected in the real world, and then what did I do with it? I cut it up into training and testing, right? Mm-hmm. This is all going to be based upon training error, meaning that I can only learn from the examples that I'm presenting the model with. All right, once again, you can't utilize testing information or testing performance in order to apply this updates. I think later on you guys will understand that even if I tell you, think about it from this perspective. What does the model currently know with respect to the error assessment? It utilizes or knows the cumulative sum of the individual deviance and error for the entire system. And then it establishes the weight backpropagation via just the product of that error relative to the inputs. Here's the interesting part of it. If I gave you the error for the training, or for the training error, right? That's the one you backpropagate on. Then you can go back and you can adjust for the training error. What if I gave you, even just gave you the actual performance on the testing data? I just gave you a number. I didn't give you every single label, but I gave you how well you're performing at a whole on, in general, mean squared error on the entire set. It's still informed, meaning that you could actually go back and backpropagate that error as well, okay? So all you actually need is just the error of the system, right, in order to be able to determine whether or not you're converging the solution. The model can even be corrupted or a little bit skewed by allowing it to see data it shouldn't see. So we have to make sure we keep that, that testing data fully away from it, okay? Here's an interesting portion of it. We will use testing performance in order to do what I talked about early on in the class, which is the concept of early stopping, right? That's the stop before the model starts to overfit. Mm-hmm. So even though I'm not providing the model with the exact values of where it's going within terms of the data set, I'm actually going to need an additional data set to keep even that small amount of information, right, just knowing where to stop from being integrated within the process. You have to be very careful, because if you don't and you let the model see too much data, these things have so many free parameters. They are so flexible, they will consume that and they will integrate it, okay? And what happens whenever you start fitting to all the data? The actual level of performance it has in the real world, the utility of the model becomes totally moot. You have no idea how it's actually going to perform because it has seen things it's not supposed to see, right? Even if it just saw the test key for a minute, right? It's still not a good test anymore, okay? So, like I said previously, every one of these individual gradients is locally computed. So we can only assess the gradient at the local compute point. This matters later on whenever I'm talking to you guys about utilizing that Jacobian of the gradient system. Okay, this is already on the other slide. I think I was just covering it again. Here's my structural notation slide because I want to make sure that I'm clear again with this, all right? There it is in gigantic letters. Okay, up in lights. The weight, okay, W. I use W sometimes. I'm going to use theta other times, all right? You can even use phi. I've seen a lot of different both letters and Greek letters utilized to represent the weights. It doesn't really matter because you'll get used to this idea that what you're seeing when you see a weight, it is a connectivity, all right? I think the notation actually implies the transitivity of it as a nodal interconnection. Because if we look here, we have two subscripts, right, and one superscript. I told you beforehand. It's kind of crazy, right? You got a lot of compact data happening there. But why do we need it? Because once we get it into the matrix, in order for us to visualize where it's at and where it's co-located within this space, we're going to have to be able to know what layer we're talking about, right? What it connects to relative to that system. So the source neuron, this is the source neuron's number with respect to the target layer, right? So source neuron layer, source neuron number, target layer, where it's driving to. So when I said originally, it's about position, right, and destination that is going to be the most critical to our understanding of the system. We do source neuron number, source neuron layer on the bottom, right, and you're effectively sort of reading in from the outside, right? Number layer ends up with this condition where this is neuron, or this is element 2, right, of source layer 1, right, and this is layer destination with respect to the system. So why do we say 1, 1 in that source? Well, source neuron layer is still going to be the first layer of the system. We often will designate this as L2 or L minus 1, right? So we just say which direction we're feeding from. If we think about the output layer as being placed in by L, target layer consideration is where it's pointing to. okay? What might I actually say on this notation? I could actually put that as layer 0 for the input. So some people start counting from 1 for the layer number, and then the destination layer is enumerated separately. So here's the part of it. Input layer, right, and hidden layer have different counters. I try to not make them do that in some cases, but some people will do this. I'm using this picture because I use it in another segment in notation, but this is the first hidden layer, right? When we think about this as a source layers start counting from the source layer, right? And then the target layer is the hidden layer count, how many elements forward it's going in the system. So this is the first hidden layer in the system. What's noted here is target layer, A2, right? This is because it is targeting layer 2. This actually, the reason why I say that this number here is probably the one that's pulling somebody off or might pull you off and what was confusing earlier on is this could be, if you were to say source neuron layer, right? You could say that would be not, that would be layer not, or the first, the input layer. But notice what happens. It is transit destination, right, relative in this case, and then transit number. I like to say that you can think about this more as the target number of where it is going and the neuron it comes from. That's the reason why when I said that earlier, I was trying to explain it that way. I was trying to give you a little bit of shorthand. That is to say, this is element 2 pointing at 2 in layer 1, right? So element 2 pointing at 1 in layer 1. Okay, so it's more about where the vector is headed than it is about where the vector is coming from, because you can obviously tell relative to the numericals of the predecessor that you're going to have the dimensionality of the predecessor feeding into the successor neuron. So in a fully connected network, that is a network in which every weight feeds in from every connectivity of the outputs of the previous layer, you're going to assume that this activation 2 here component, which is the summer and activation for the output of the previous layer, is actually going to have a weight and connectivity, right, positional connectivity for all of the previous input layer. Any questions so far? You look more confused, and I feel bad about that somehow. Yes, what?
I'm confused between the light color one and the dark blue, navy blue one. It's 1, 2, and 2, 1. Why?
Where you at? Which one?
No.
You said, 1,
yeah.
2, and
2, 1.
oh, 2, 1, and
yeah.
1, 2. Okay, so this is going to be your position target and layer target. Is that reversed? Did they reverse this?
I feel like this corresponds.
I
I feel like this corresponds to what you said earlier, where like that first subscript is which element in that layer is pointing to. So like that blue
Okay,
theta
hold
2,
on.
1 is pointing to the second element, and it is from the first element.
It's target, okay, let me go back here and make sure I'm clear with you guys on this one. Target layer, okay? This is the weight, not the core activation number. They're two different things. Activation numbers are going to have a different notation because they're going to contain their layer number, all right? So activations are going to contain layer target. So when it says activation layer target, this is saying activation for 2, right? And it's calling this target for layer. Its layer number is still going to be 1. It's still in the first layer. It's the notation for target versus the notation for layer count. So when we're naming the vector, right? When you think about a vector in general, what do you think about in terms of the vector? It has a magnitude and a direction, right? Mm-hmm. So think about the notation consideration as largely concerning itself with where it is headed, right? But also with respect of where it is started from. So in the consideration here, we have source neuron layer, And one of the problems there is I think source neuron number and source neuron layer, they might have, I think they might have reversed this in this particular notation, and I don't like that because I was thinking that I had it right with respect to the way it was set up. Okay, so there's two ways you can do this, and that's problematic. Here's another problem. I'm telling you seriously, there are two ways to do this. There is an electrical engineering notation, and there's a computer science notation. Okay, computer science notation uses a second characteristic. I think this is more of the CS notation, which places the node and origin. That's the one I tried to describe to you last time. All right. So let me say this. These are two examples of two ways to go about the process, and they shouldn't have been because I should have tried to make this notation clear. So let's do this for sheer structural stupidity's sake. Okay, I'm going to drag this over and say, if you make this the source neuron and this the neuron layer, and you place a comma between them, problem fixed.
Yeah, now it makes sense.
Now it makes sense, right? So what's the issue here? Why
It's going back like.
Why electrical engineering versus computer science notation? You guys know the whole thing about jargon, right? The whole concept of a discipline is just about the right to use different jargon, right? So notationally, now what I've done is I've committed myself to having to use one notation for the remainder of the classroom for purposes of making sure we're 100% certain of operational conductivity, okay? So that means that I have to restrict the sources that I utilize for visualizations because, as commented here, I am able to look at this quickly and think about it and go, oh, okay, I see the origin destination number characteristics, right? I see 2, because I see source destination, right? Because I read in from right to left. And so when I'm looking at it, I go, that makes sense, right? Source layer position, right? It says source neuron layer. And when we say source neuron number, what if I flip those around in every case? Layer number, number layer. Really, does it matter? Hold on, track with me for a second. When you see this in matrix form, think about this as a set of weights, right, along that process. You have inputs, that's one vector, right, and you have weights, that's another vector. You compose those two vectors together, what do you get? You get a square matrix, which is going to be composed of the element and the weight, right? We know where it goes after that. We know one of those goes to every element in the subsequent destination layer.
Yeah.
So whichever notation you see here, all right, and I played around with this just to be able to do this, because I'm going to tell you just like this. Once you see it, when you read it, you're going to see the process, the flow process here, okay? Let me keep going, even though I know it doesn't feel like it's fixed, because I'm going to talk to you about how this is put together, and we're going to look at the layer and weight count components, and you guys are going to see the reason why. Once you see how it goes forward, you'll see that either one of the notations is going to be working. Layer always goes on the top, all right? So that's one thing that keeps us from any level of abstraction. What goes in the front and what goes behind and the bottom is entirely up to you depending on which direction you count from, whether you're counting from the back or whether you're counting from the front. When you're counting from the front in front prop, you're counting for forward propagation as the multiplicative layer. When you're counting for the back and back prop, you're counting from layer -1, what's going back into the previous state. That's the reason why when I say I read right to left on the numericals in the bottom, that's the way I note them when I do my back props, okay? So let's just talk about it visually and flow-wise, and you guys will, I think, get through the process of this notation, what I mean as far as how to count from the bottom. Why is this a high-level topic? Anybody want to figure it out? Anyone want to figure out whether this is an upper level, 67 level, 55, 67 level course? Because it's not fixed yet, like everything else is. It's still in process. It's still in flow. There's a lot of stuff that still needs to be worked through here. Let's think about the concept of just two neurons in direct sequence with one another. As a result, we have an input, we have some hidden neuron within the system, and then we have another output neuron. What is this? This is that same workflow that I was showing you beforehand. I'm going to use the relationship between these systems to iconify activation 3 is what? This is the activation level of the final output of the neuron, right? So it is activation on, it's sigma activation on the Z for the input of the previous elements of the layer, right? So we're just going to call that G of Z, all right? So what's G here? G of Z is the activation function. This is just the output of the numerical here. We're going to say that this is activation, or alpha. Everybody tracking? Okay. A is given what? Layer notation 3. Why is it the third element in the system? Why did we start counting from 1 for the input layer? Because the input layer goes through a series of weights, right?
Right.
It is effectively inputs, weights, integration. Inputs, weights, integration. Inputs, weights, integration. Depending on however deep you want this to go. It's always going to go that same system. Every layer treats the layer before it as if it is its feature vector. So from the most basic standpoint, a single layer neuron will have the same process of determining the relevancy of the weights with respect to the integration of this output, G of X, or G of Z, excuse me, with respect to this consideration that the activation at that layer, Act 3, right, is as a result of linear combination of elements Z3 for what? The weights in 2. What is that weight 2 there at the bottom? That's just the second layer, all right? Why 2? Because that's showing what is being brought through. So if I said what's being brought through in that first consideration is resultant to or considerate of Z of 3, right? So Z3 is a result of the products of what? Activation in layer 2. So the activations in layer 2 become the inputs. These A's here, A2, become the inputs through that weight matrix in order to become Z. These go into the activation in order to become the output of the system. It's a chain, all right? That's the reason why we can use the chain rule. It's a bucket brigade, right? I do the thing and pass it off to the next person in the system. Now, if I restate this relationship between the output at A3 and Y as that same D minus D hat or D tilde, right? The estimator, given estimator characteristic. What am I working with? Same kind of calculation we were previously. And I said previously, if I take the partial of J with respect to the weights in the system, right? I need to know how much those need to change in order to be able to minimize that J theta or JW matrix, all right? Whichever we're going to call that, the matrix of weights within the system. Performance in general can be broken up into a couple of different areas. Where I say the partial with respect of the Jacobian of weights with respect to the activations at 3 is the first component, the prop. The second component, the prop, will be what? The relationship between the activations at 3 and Z, that is the components that make up that activation. Now, what do I say? The activations at A are what? A consequence of the weights times the inputs of the previous layer. So if I keep treating this, I keep going back, you notice something. The inputs at that third layer relative to the outputs of the second layer are partially responsible for and partially contribute to the makeup of the whole of the error with respect to the second activation, or the weights in that second layer component. Notice something. The numericals on this example also not perfectly consistent with the other notation we were dealing with. Why is this problematic? Because I'll tell you just like this, go looking for neural network notation anywhere on the internet and you're going to find one of like 3 major notations. All right, so that's the reason why I'm saying I try to create one consistent setup for you, but even in the explanation, what have I done? I've made it plain, okay? So the more I try to explain it, the way the worse it's going to get. But just keep in mind, if the notation is consistent, it should still describe the process. That's all we're really looking for here. We're looking for one standardized methodology. So, whenever you guys write it out, as long as it's internally consistent and I can track with it, golden, okay? Also, the other consideration is indexing processes in different languages have different count points, right? So what the row column notation can be flipped around between different systems and syntaxes. So when you're putting it together, just try to make sure you're tracking that your notation, how you've sort of set it up on paper, and how it's going in to be calculated in the system is making the same sense. So if I've propagated back for and calculated the relative relationship between each of these individual components for this first segment of the system, what I need to calculate next is the relationship between the activations at A2 with respect to Z3, right? Because that component makes up, activations for Z3 are made up by A2s, right? Mm-hmm. So A2s become, by multiplying A2s times theta 2s, I get Z3s. Goes through that process. So I know what theta 2's components are, and I can backtrack through here. I can say that zeta 3 is with respect to A2, A2 is with respect to Z2, and Z2 is with respect to theta 1, right? We've tracked all the way back. We've rolled through the whole process to determine that the relative performance surface here at activation A3 has partial responsibility all the way back to the original case. Now, this one's slightly longer than the one that we looked at with regard to the shower one, but not really, because we condensed one of the notational characteristics, because we said that we used error as the notation over here for final error in the system. This says what? What is this error right here? These two errors are the same thing, right?
Yeah.
And they are, in fact, that error up there, right? It is J theta with respect to A3 theta, right? So when we're looking at A3 is respect to theta, then we say that each of them actually composes or holds a certain amount of responsibility for the error. We also say that responsibility is a product. We also say that the product is a result of the chain sequence pushing all the way back. So we have components in here that are actually similar to the components that are present later on in the system, such that Z relative to O2, right? We have Z2 relative to O1. This is actually similar in the respect of saying this is Z at that first layer output for the system, relative to O2 for the inputs weights. This is Z2 with respect to O. Notice what happens here at the end of the process. It says that the partial of the total error, total gradient for the system for this set of weights, or that weight itself, is independent of, or can be calculated independent of, the components for the second element. Now, what elements do they share? We have A3 and we have Z for the activations, right? So why in this initial case are we saying Z activation here, just Z activation? Should that be a different Z? Or is that the correct Z? Right, it's still Z1. Is it Z1? Partial Z of O2. What is it? What should it be? I saw this one when I was looking at it earlier. Sometimes there's errors that I look at it and say, well, I could fix that, but I could also look at it. That's A3 of Z3, right? With respect to the notation we put forward. So this says that this should be Z3 with respect to O2, relative to Z3 with respect to A3 with respect to A3 for J of theta 2. Now, what happened with the bottom segment? It's flipped around, it has Z3s in it, right? Now it still has Z3. Well, what happens if we put Z3 with respect to A on top of it there? We would actually have the inverse here. We'd have Z2 A3, right? We have A2 Z3, but we also have Z3 A3 here. Z3 A3 would what be present here, right? Z3 to Z3 of O2. So that actually means they contain the same elements, or at least contain some of the same elements. Let's go forward to the next segment of the example, because when it gets a little bit more complicated, you guys are going to see, I checked this one over a little bit more thoroughly, and I think the notation is more clear. Whenever I have linear combinations, activations within the system, right? If I say ZCOM for this framework, where is Z in here? It's not, okay? So that's the reason why whenever we look through it, we can see that it's not present in the system. But when we look here, we say J not A3, that's the first component here. And this says what? A3 to Z, that should be Z3. It's obvious, it's up here in the notation, right? So we've given that, it tells us, the lines tell us what it should be. The lines tell us what it should be. So, reason why I'm saying this to you is even if the notation is off, you can still go in and look at this from the flow and see what makes sense, all right? I apologize for this because I did not have time to fix it by the time I saw it. All right, so what I'm telling you is sometimes errors can, as long as explained in concert with what's being discussed, they can be shown as like, okay, why doesn't this make sense? Why isn't this tracking? So this set of slides is not my favorite so far. Not my favorite so far today. All right, recombinations. This one actually makes a little more sense because we say A2 with respect to Z2 is here. So we say Z2 with respect to activation 1 becomes problematic, right? So activation 1 is over here. How do we have partial for activation 1? It should be activation 2. Once again, another notational error within the system, all right? So I'm going to go forward, we're going to the next one. This one actually fixes it, or at least mostly. I haven't found any true errors in the system. What did we say with the first layer, right? We said the first layer is that each component takes in a set of inputs for that layer times the weights, right? And becomes that linear recombination Z. Linear recombination Z given here, it gives you the full recombination, right? And then indicates the activation with respect to that layer component. Now the notation on this one seems consistent because we say Z1, right? We say Z1 for component layer, right? That's saying Z1 to layer 2. And we're treating the first layer as layer 1. Now, should it be Z sub 2 and not 2 in the brackets up above? Why is it saying Z as the layer 2? One would make more sense. This 2 right here would make more sense. Because Z2 makes sense, right? This is the target layer. If this is the layer number of the actual layer number within the system, this should be the first hidden layer, right? So its destination is 2, but it's given as the first layer. So it depends on whether we're counting here from 1 or from 0 with the layer numbers. So, what do we notice? It's not going to be that much harder for us, to be able to calculate the relative degree of errors, but how many more weights do we have? We had 2 weights previously, right? We had 2 knobs. How many knobs do we have now? Well, we have 2 by 2 in the first layer, right? 2 inputs, 2 neurons, 2 hidden. So that's 2 by 2, that's 4 at the first layer. So we have 4 adjustments at the first layer, 4 adjustments at the second layer. We have a total of 8 knobs to crank here. So imagine this is, your shower is over here somewhere, right? Your neighbor's stealing some of your shower water, right? And you know, then you've got like some upstairs neighbors that are distributing their water as well, and then you got the main down here with a splitter on it, okay? That's what's happening. That's how complicated this system gets in saying, what knob do I need to go crank in order to fix this problem? So, we're going to talk about a couple of pathways through this, and I'm just going to walk through these. And like I said, I will go back and try to definitively fix the workflow of this such that I have one example that shows you numericals that I've fully vetted for operability, okay? Because like I said, I look at these and I go, okay, that makes sense. Because I'm not really trying to count the numbers, but when I walk through it with you guys and I go, wait a second, what is that number doing there? That doesn't belong, okay? This is complicated, there's a reason why it's complicated, but I want to try to get this as right as I can for you. I spend an inordinate amount of time looking for good examples online, and then these people just crap at me. No, somebody put out a lot of effort to do this, obviously, right? And so I look at it and say, hey, thanks for doing that. I didn't have a lot of this stuff whenever I was coming through. These are my actual notes for when I took this class, right? So I had to just write everything down for this. So, you know, I didn't have slides for it and all this fancy stuff like you guys do. I had to sit and take notes. Because when I was taking, Dr. D just came in with a whiteboard marker and just started equations on the board, okay? I still might do that, who knows, it might happen at some point in time because it might work better, but let's look here, we have two pathways. So what we're gonna do is we're gonna consider that we have two targets, and each of those targets will be made up of Z1 in the first configuration, Z2 in the second configuration, right? So we have some output activation, A3 for Z2, and A3Z1 for the activation relative to this system, such that we have some target Y2 and some target Y1. This means that we have multiple ins and multiple outs. This is a little bit more problematic. It's harder for us to figure out one singular gradient with respect to the system, right? Because now, in fact, there are more than one gradient. Because there is an error with respect to the second element in the second layer with respect to Y1, right? The first target, and with respect to Y2. So if we wanted to determine the total relationship here, if we just wanted to look at these two weights, these two pathways, look at first at the pathway that contains elements within the orange bracket. Okay, let's see if this one tracks properly. So Z for 1 forward relative to layer 2 with respect to theta 1, 1. That makes sense, right? That one tracks. Then what's the next element in the system? Activation A1 with respect to Z1. Okay, Z1's correct. That tracks. Then activation Z2 with respect to A1, that tracks. Then what happens? Activation A2 with respect A3 for Z3 J theta, right? So it says for the first element in the system, working back from the origin, right? I can see that the total error in the system is responsible, these are all of the responsible parties for error received at A3, or excuse me, activation 2 for layer 3, all right? Activation 2 layer 3, there's 3 there. Activation 2 layer 3 is what? Y2. This is the error with respect to Y2 for the pathway calculated through only the input layer or input element for X1, right? If I make up the components now for the second activation, we say what? Z1 at layer 2 for 1, 1, layer 1. Okay, that one still tracks. Z2, usually your first question is what? Whether or not these are set up properly is just to look and see if the adjacency actually takes into consideration the chain process. So, at the end of this chain process, I should be able to cross off all of these systems such that I leave this theta and this weight at the end of the process. Notice what happens there. I have basically said that if I take all of the other factors that could be potentially relevant to the system, and I set them all equal to one another in that gradient space, that I can create a cross-cancellation matrix, cross-cancellation assessment, where I can directly link the output to the input of that particular system, or at least the sensitivity of that input. So now we have one set of, or one weight, and we have that one weight's contribution to the entire area of the system. Right now I have what? Partial of theta in layer 1 for element 1, 1. What is the 1, 1 at the bottom? 1, 1. input 1 to element 1 of the destination node. All they're talking about is element, destination, layer. Everybody tracking with me? See the reason why it's fixed? You can do it in your head. You understand what they mean now? So once you get the picture of saying that I know which weight I'm concerned with, and I know it's made up by two different, or it composes two different pathways, I'm saying that the relative contribution of error to the entirety of the output of the system, this is one weight. How many do I have in that layer? I have 4, and I could do 4 of them, because 4 of them compose. So what does that start to look like? Everybody want to go through those with me?
So when we talk about a universal approximator,
Mhm.
is that, because that's assuming like one hidden layer, but you can have multiple neurons, right? And is it?
It only requires a single hidden neuron in order to be able. I'll do the proof for universal approximator. I have a set of slides for that proof too. Yeah, the main thing that we have to prove is that there are no conjuncting functions, or there's no spatial operating functions that can prove the ability of that surface false. So we only need one neuron in the hidden layer. You can have multiple inputs, but one neuron in the hidden layer in order to recompose the makeup of the layers from the first layer of the system. So you really need 2 sets of weights. You need the weight in the first layer here, right? And then you need the weights in the second layer on the output. Even if you only have one weighted output, now you have a weighted appraisal of the features from the previous layer. Remember previously, in order to be able to create the circle, right, to be able to find the circle in the center, we could make a triangle, which was made up of 3 inputs, and we only needed one neuron to do that. We only need one neuron to take the 3 inputs from the 3 linearities to be able to find the cut points, the clip points, for the edges of each of those portions. So that's the way in which we use the universal approximator notion is that we're carrying forward. But I will do the universal approximator as a proof, and I'll run through the whole proof for you guys. So let's look here real quick and we say, second layer parameters. Why am I concerned with second layer parameters? Because they're actually smaller, right? Second layer parameters are smaller because I only need to take into consideration just the elements that directly lead into them. So if I want to know the partial, if I want to go up here and think, partial of theta 1, 1, 2, right? Or I guess you could say theta 2, 1, 1. This element is this element, right? This element is that one. This element here, right? Excuse me, this element here is that one. This element here is that one. This element here is that one. Okay? So allocate those as you see fit, right? This one here and this one here. Why are these two grouped together? Because they're the inputs for A31. So we would think first about what are the weights of the inputs of A31. Because if I wanted to determine the relative level of contribution, I need to take A31 in each of those cases. A32 is in each of these cases. Right? It is the error with respect to what is intended for this output relative to what's intended for this output. So these 2 up here on the top will be for this output. These 2 down here on the bottom will be for this input. So notationally, when it counts 2, 1, and 2, 2, and 1, 1, 1, 2, it's counting the elements coming into the target element of the layer, right? So it is from where to where, right? First one is saying element 2, 2, 1, right? Element 1, 2, 1, giving the target. And you can look here and you can just see linking together Z as a summation of products relative to the activation at that element, okay? Notice this and this are always going to be the same, and this are going to be the same, right? So when you look at this ratio here, you're going to be looking at the first term, should be on top of it, should be the Jacobian of partial Jacobian for that particular weight, right? And then the weight at the bottom should always be out here, at the bottom of the system. Technically, the element that's at the end is the element that's kind of closest in, I guess you would say, in terms of the product relationship. But we tend to think about it in saying that if Z1 is relative to 1, we need A1 relative to Z1, right? So if you wanted to start writing this left to right, think about saying the relationship of the error with respect to the activation at that layer, with respect to the activation at that layer, with respect to the products, the sum of the products, right? Or the sum of the products with respect to the weights they're made up of. Guess what you did? You can actually do that as a matrix combination process now. We can treat it as a vector times the array transform. Because we can take the weight array, right? And then we can do a element-wise multiplication of the weights times all the inputs for that array system, and then calculate the entirety of the gradient for the estimator. What does the second layer look like? Is it still intimidating? A little bit, but maybe not as much, right? So if I'd shown you this slide to begin with, what would have happened? Immediate abstract panic. Okay, that's how I feel about these a lot of times. I put them up and I go, nope, they're going to panic. You're going to see this, they're going to panic. Okay, but I want to build up to the point where you say this is like the equivalent of books making up, pages make up books, or chapters make up books, right? So we have pages, chapters, books. That's just a composition, just how to read it going forward. It's a forward process. Now, from this, what happens? Since I'm able to calculate this relationship, all I have to do is plug it into that gradient backprop calculation and then do what? Adjust each one of those values now in order to try to minimize the error. Run the whole thing again, right? Determine the new error as a result of that previous assessment, and then guess again by a small amount and see if I can fix it. So while we saw that process of the ping pong ball come into rest at the bottom of the skate park, right? Imagine that happening in 8 dimensions simultaneously, right? You have 8 ping pong balls in an 8-dimensional surface, all of them coming to rest at the absolute bottoms of wherever their gradient level surface sits. If you can imagine that in your head, you're a better person than I am, but the reason why I say it is it's just that same process several different times, or several ways simultaneous. Interesting part about it, though, is as we said that this is a partial surface such that one weight combination may actually change a little bit of the weight combination the other system works at. So if I change the main and I change the handle, we notice that their abilities to find their relative bottoms adjust, such that you have to keep bringing some of the things down to keep finding a better ideal minimization for the entire gradient. There isn't one global minima for respect to all of these elements simultaneously, right? There is some global minima for the entire system. What's the real problem with it? We are never going to know what it is. This is the one thing that I look at and say is probably the most challenging aspect of it. You can train a neural network, and then you can press reset on it, and you can train it again, and you may get an entirely different set of parameters in the result of that process. Right? So we'll talk about it a little bit more, but when I said previously, and I mentioned to you guys beforehand, these values that make up the original system here are randomly selected to start off with. So whatever the randomly selected seed that initializes the values for that system will determine how close the actual values are to the ideal value conditions. If each one of these are a ratio of the weights relative to that layer, we're going to have 2 layers worth of updates that we're going to have to attempt to try to find some ideal set of weights. Your data set will only allow you to be able to converge to that ideal set to a certain degree of minimal error, right? And from training to training, that degree of minimal error will actually change. So we're going to get as good as we can get under the circumstances, and we're going to find a solution that's I often say the one that I've been given, which is say a 90% solution today, or is 70% solution today is better than a 90% solution 6 weeks from now, right? So the solution that is approximate and workable now is much better than attempting to try to find the ideal, perfect, total system solution for this, because this is a workable, viable solution in the near term. Now, what is this going to help us do whenever it comes to making up bigger, better things? We're talking through the math. This is the part that gets a little boring, but whenever we get done with it, we're going to talk about how this helps us do things like computer image analysis, right? Human subject identification. You can annotate images, right? All that stuff is actually made up of a expanded, massively expanded system. So this goes into a matrix, right? And then you have matrices of matrices, and you have matrices of matrices of matrices, right? And this whole thing just zooms out. It gets fractal, fractal, fractal. You can keep doing this and keep expanding this for a network. What do you think this looks like when it goes deep? Deep, I'm talking 6, 7 layers deep. I could not fit it on this slide, all right? The smallest font that we could possibly get readable would not fit. But what we realize is that we don't have to do it by hand. We just have to understand that this is the process by which this whole workflow happens. And I would say you probably have enough knowledge now to say if it doesn't do exactly what you're looking for it to do, if there's something that's kind of missing here, there's not a whole lot else other than these primitive elements of this system that we need to work with in order to be able to construct an optimized perspective on this system. All right, I'll let you guys go. I'm sorry once again, I missed my time. I will put out like I said, I'm going to put out a link for you guys to be able to start on implementing this in code. All right, so we're going to start off with training a neural network in code. We're going to have a simple problem, and then we'll later on, as soon as we get done with that, we're actually going to start on developing, utilizing some of the standardized libraries. All right, so we're going to start off with, I'm going to let you guys have your choice of TensorFlow or Torch. Both are going to be, we're going to be able to build with Keras with both of them. All right, Keras, I'll talk about Keras and what it is and how we compose layers and what those layers look like. We'll start talking about the definitions of the layers and how they make up the capacity to be able to chain together operations that build more elaborate functions. And along the same time, I'm going to actually go through and do a bigger composite of this system. I'm also going to fix the notation on the first couple of sections of the slide, because these are correct. The other ones have some issues with them that I have to fix. Okay, thank you guys.
So, I have a question. Like, can they use the lab or the VS Code? Like,
For what? Oh, honestly, a lot of that stuff wasn't even around when I did this. So Google Program might be able to allow you to run payloads without having to do anything.
I forget everything like that. I didn't. Yeah.
VS Code's a
But
lot
there
of
was
VS Code's a lot
I
of
tried this one before.
it's very heavy. It's very bold.
I feel like I need
There's a lot of
something to get my teeth into, you know?
I just use Anaconda.
I'm thinking like, 'cause if I can get it, like, if I can get it in code, like the perception, like
It's just
because that's the hard part. Is like I understand the forward propagation
I just
because it's basically you're just
saying you can
you're just multiplying things, adding multiplying things. It's the back propagation that's throwing me off. 'Cause I'm not getting
I'm gonna pop you guys a Docker and let you container. We'll use execute with Docker. So one of the hard problems that I have right now is getting Docker to
I think seeing the code will help a lot.
It should be. I think I went through everything. Yes, please. Say again? Go up here.
I thought that there must be 2 times for security. There must be 2 because if you do that like that, it's the same and it's the same. It's a multiplication.
It's 2 products. So it's a summation of 2 products.
Yeah. So like if you like eliminate all of them, like it's similar. And also this one is like. But if you sum 2 like same amount, it must be 2 times the left.
So look here. Activation relative to 3 to 2. activation relative to 3 phases. No, so activation 3.1, right? So activation.
Yeah. I haven't used that.
Activation 3, this is elements of the activation at the 3rd layer. This is the second activation.
What is the?
The three of us.
It's the part of the part. It's a division, it is a type of, it's a division, yes, yes.
Whatever the
Yeah.
scope is.
Like,
They said most of the work that goes into it is, because it's
Correct.
really.
so,
Are you familiar with the chain rule of calculus?
yeah.
So these are DXDVs, they're partials, so they can be canceled. Do you see what I'm saying? They're not, they can be canceled if they're full products, but they're partials. So we're using DXDV to be able to use the chain rule with respect to this, saying the partial with respect to Z2, right? That makes this product relationship the relationship for theta 221 to partial A22. Because if you take the product of partials, you end up with just the ratio of components.
Delta, right?
It's usually really.
It's actually not a delta, it's a stylized D. So partials is a stylized D, the delta is the actual true D. So the difference is this. This is, if I was to take the derivative of something. So I took the derivative of J with respect to the weights,
Yeah.
right? What is that? That's the whole derivative, that's the whole J. Whenever I'm thinking about it, I can say the partial of J with respect to the partial, or the partial of, and notice these are little stylized D's, right? Of W, but I have to instantiate a W. All right, so I could say W, I could say W star, and maybe this is the matrix form of W, right? It's the whole weight system, okay? But I could then also take consideration for one element of the system. Now it's just the partial of one element. That means, what is the respective, the error with respect to this one piece? So if I ask a survey in the class, and everybody provided me with a numerical estimate, some people would get it wrong, some people would get it right, or some people might be above or below, whatever else, right? I say, what is the total error in the system with respect to Cheyenne, right? With respect to his individual guess. I could chain back how he made that process to determine how the total error of the class was related to one person's estimate in the system. This is the sum of product between two pathways, the upper and the lower pathway. This would be in the pathway that indicates the second output, or the relationship of 2-2 with respect to the second output, and this indicates the relationship of 2-2 with respect to the first output. A1 in the first output in green, right? This is green, and this one is the yellow at the end of the process. They look the same, but it's just the difference of elements, what the elements are pointing to.
This is the number of the Newton, or what is that?
Correct, that's the weight number. These can be W's as well.
Oh, yeah.
The theta can be represented as W as well. I wish there was one thing. I feel bad because I started off with one set of notation and I was trying to keep it consistent. And then I realized in my old slides in the website that I'm